thank you very much to everyone for to the organizers for the workshop, and I hope you guys can see my slides. Yeah, can you see them? Yeah, yes, you. Okay, sounds good. Thanks. Yeah. So thanks for the kind introduction too. So yeah, so this talk is about some recent progress that we have made over the last 2 years on correlation clustering, which is and it's very pleasing. I mean, I think I'm very happy with this talk because it has both a theoretical component and a practical component, and we have two different results. One that is very deep in the theory, one that is very useful for practice. They are not quite matching, but it's like a general talk. Like they go together in the talk still, so I'm happy with it. Feel free to interrupt if you have any question. Yeah, if something isn't clear, it might be a little dense, but like feel free to yeah, call me up. So okay, so this is a joint work with a lot of people, like because there are two papers. I'm going to present two papers. So yeah, amazing co-authors that I'm very lucky to work with. And the talk is about clustering. So as Ula said, like, clustering is the following problem. You have a set of data elements, and you want to partition these data elements so that similar data elements are in the same part, and dissimilar data elements are in different parts. And of course, you can have the view that Ula took at the previous talk, which is the similarity between the data elements is given by the distance. Like if two data elements are close, they are very similar, and if they are far, they are very dissimilar. So you can just look at the metric space and try to partition the metric space. Here we have a different way of seeing it. We will have the notion of like we will know in advance whether they are similar and which one are dissimilar. We have this precise information, and this is a setting that takes place, like for example, in a social network. Like for example, if you have a friendship, if you have a friend relationship between two persons, then there is no really distances. It's just like there is an edge or there is no edge. So they are similar if they are like they are friends, or dissimilar if they are not. Or you can also see it as like your preferences if you order some or if you look at if you watch some movies, like the movies you have watched and you have liked and the movie you didn't like, and that's some kind of similarity you can infer from this. Okay, so the clustering I'm going to look at has motivation from like partitioning social networks, for example, partitioning the World Wide Web where there are like direct connections, and partitioning with the motivation of finding communities, group of heuristics, compression schemes, so different things. And so the objective we have, and let me spend a little bit of time on this objective, is the following. I give you can see it as a complete graph. So your data elements are the vertices of this graph. And now, there is always an edge, and this edge is labeled plus if they are similar, or minus if they are dissimilar. Okay. And now your goal is to partition this graph, the vertices of this graph, into as many clusters as you want. You have no constraint as in the previous talk where it was k, a fixed parameter, a parameter. Here it's arbitrary. You can partition in arbitrary number of clusters. And your goal is to minimize the number of plus edges that are across clusters and minus edges that are within clusters. Okay, so for each pair of elements that have a minus edge, if they are in the same cluster, you will pay 1. For each pair of elements that are in different cluster, if there is a plus edge, you will pay 1. Okay, so we really want to minimize the errors you are making with these elements. Okay, that's exactly. So just gonna make a little simplification just for the sake of this. So it's a complete graph, but let me just think of the plus edges as the edges, and the minus edges are like are no edge. Like it's like I just look at the complete graph induced by the. I just look at the graph induced by the plus edges. Okay, so my graph is really complete, but let me forget about the minus edge. And when I talk about degree, I really mean the plus degree, and neighbors, I mean the plus neighbors. Okay, this is for the sake of simplicity of this topic. Okay, so what's the literature on this? So there is very beautiful. So there have been like constant factor approximation, and I think like there are like two big results from a theory point of view. One that has been very influential, that is called this pivot-based three approximation algorithm by Elon, Charika, and Newman, which consists simply in like, you pick a random vertex, you look at all the plus neighbors, all the neighbors, you put them with this plus vertex, you make a cluster that's one of your cluster, and then you repeat on the rest. Okay, so it's a very simple algorithm. It gives you a three approximation. Very simple. And then there is the best known, this is our challenger for today, which is the LP rounding algorithm, which is the following. So you take the LP relaxation and then you round it using a pivot-based approach that I will discuss later on. But essentially, you can get better than 3. You can get 2.06 approximation using the work of Chawla, Makarychev, Schramm, and Yaroslavtsev. I'm going to go a little more into this later, but this is like the best known result so far. And from a practical point of view, it seems that correlation clustering is really good. Like there has been like recent studies, like this is something we use internally at Google as well. It's a good model. Like correlation clustering is definitely a good model for doing graph clustering, for community detections, for different purposes, data mining purposes. And so it seems that we are really interested in getting like efficient algorithm, practical algorithm, for correlation clustering. Okay, so the correlation clustering objective has this nice property that you don't have to know in advance the number of clusters. Like, if I give you an input where you have k disjoint plus edge cliques, and in between you have only minus edges, then there is an optimal solution where it's 0, and you would just partition into these k cliques. And k can change. You don't have to change anything. You can just run your correlation clustering algorithm, and this algorithm will find these cliques. I mean, if it's a good algorithm, it will find this clique. So you don't have to really know anything about your input in advance. So that's a very good thing. And if you think about what is a good solution to correlation clustering, you can think of it as like the clusters are very dense subgraph of plus edges, right? With very little expansion. Like, you don't have that many plus edges outgoing of the cluster, right? Because otherwise, like, it's not really a cluster. So that's what the correlation clustering objective is essentially trying to capture. So, like an optimal solution, you can kind of see it as a collection of disjoint, quasi-disconnected, like, there are few plus edges maybe between subgraphs that are almost cliques, like quasi-cliques, like, there are many plus edges and very few minus edges. Okay, good. So this is a very interesting objective. That's what we're going to work with. So please interrupt right now if there is something unclear about the objective, because I'm going to try to continue on that. Okay. Right. So for these talks, I want to look at two questions. So one is like, in practice. So how can we optimize this objective in practice, in the sense that we want to do it efficiently for real-world inputs in various models that happen in the real world. Okay, not focusing necessarily on like offline setting, because sometimes like we have to deal with like streaming, we have to deal with like distributed algorithm, we have to deal with many things. So what can we have a general approach that can give you good approximation for correlation clustering that work in many settings? Okay, that's for practice. For theory, I want to try to get the best approximation guarantee for this problem. Okay, and these are the two questions for the talk. And because it's a theory workshop, I put the theory question at the end so that I'm sure you guys stay until the end of the talk. So I'm going to start with the practical results first. And let me try to give you a general approach that we designed last year, and that actually turns out to be quite useful. Is starting with this very simple observation. So let me start. I have this lemma that I'm gonna try to give you intuition about. Is that in your correlation clustering instance, there is always a constant factor approximation, so a constant factor approximate solution. So a solution whose cost is within a constant factor from the optimum solution. That has a very good property. And this good property is that the clusters of this optimum solution, they have a high density. Namely, there are many plus edges inside. Like, 99% of the pairs inside the cluster have plus edges. Although, yeah, good. And each vertex of the cluster has a 99% or a 90% of its neighbors, plus neighbors, inside the cluster. So if you really think about this, it's like very dense plus subgraph with, maybe a 10% fraction of the plus edges going out, but like, in terms of mass, it's like massively plus inside and massively minus outside. Okay, so I claim that there is this always such a structured solution in our, and that is good in terms of cost in our in any correlation clustering instance. And the proof of this is kind of almost immediate, right? Like, let's take your optimum solution. If your optimum solution doesn't satisfy this, then take one cluster that is not very dense in terms of plus edges. Then it means that inside you have at least 10% of the edges that are minus edges. So in fact, you are already paying like 10% of the total number of edges in that cluster in your optimum solution. So if I don't care too much about the actual constant that I'm going to compute, I just want a constant factor approximation. But if I don't care too much about the exact constant, then I can say, okay, I'm already paying like 10% times the number of edges inside. So I can put everyone as a singleton. I can completely break down this cluster into singleton cluster. Okay, and now I'm paying the plus edges, but the number of plus edges is at most 10 times the number of minus edges that I had initially, right? So I'm only losing a factor 10 in approximation guarantee here, right? I had 10% of the internal edges that were like minus. I make everyone a singleton. Now these minus edges, I'm not paying them anymore. I'm only paying the 90% plus edges. So it's a factor 9 between what I was paying before, which was 10%, and what I'm paying now, which is 90%. So if I don't care too much about the precise constant, maybe I'm losing a 9 approximation here. But now I know that if this happens in opt, let me break this cluster into small clusters. So I only care about clusters that are like extremely dense. Okay, it's same thing for the second property of the lemma, right? The second property is saying, okay, if I have a vertex that has like less than 90% of its neighbor inside, it means that it has 10% of its plus neighbor outside. So it's already paying 10% of the total degree. So I can make it outside as well. It's going to pay just like the whole degree. It's like 9 times higher, 10 times higher. It's not that big of an issue. So I can do that. So I can really modify the optimum solution so that it has this very nice structure of quasi-cliques. Okay. And this is where it starts to be really nice, because if you have this quasi-clique structure, in fact, I think there is a very beautiful algorithm that is almost geometric here, because if you look at the vector, the vector of the adjacency matrix here, two vertices that are in the same cluster of this structured solution that I'm looking at, they have almost the same adjacency list, right? Because they are connected, they are very much connected to the inside of the cluster they belong to, with very few outgoing edges, which means that if I look at the symmetric difference between the plus degree of the of two vertices of the same cluster, they are extremely close, right? Like the symmetric difference should be like at most some 10% fraction of the total degree. So these two vertices, they are in the same cluster. They have very strong, very similar vector in the adjacency matrix. So it's like if I were to put them in some Euclidean space, they would be very close. The vector should have like very similar behavior. Okay, good. So that's the key insight. Like there is this notion of agreement. We say that two nodes agree if they have almost equal or very similar neighbors. Like the neighborhood set of these two nodes are almost identical. Good. So now this lemma, which is almost a corollary of the previous lemma, is Yeah, exactly. It's just what I said. Like there is this constant factor approximation such that for two nodes that are in the same cluster, they are in agreement. They have, almost similar neighborhoods up to an epsilon fraction. Okay, so that's pretty basic property so far. But then it gives this, this simple algorithm, which is like 4 steps maybe, and which is, it's a very simple algorithm, very bad approximation guarantee, but very robust. So it's going to be impressive. So it's very simple. Like so take your graph and now remove all the minus edges. We forget about minus edges. Remove also all the plus edges between pair of vertices that are not in agreement. Okay, so we know that for each pair of vertices that are not in agreement, they are not in the same cluster. So we're going to remove the edges between them, the plus edges between them. They are not in the same cluster. So opt is paying for that plus edge. So I can also forget about it. Opt is paying for it. I can forget about it. Good. So first, remove all the plus edges. Second, we're going to say that the vertex is light if at the first step, it has lost many of its plus neighbors. So it's a very sad vertex, right? Because it is not in agreement with many vertices, right? It is in agreement with few vertices because it has lost many of its neighbors. If it's in agreement with few vertices, it means that it's not really in a good cluster because it means that it has many neighbors outside of the cluster, right? Because it has a lot of plus neighbors that are not in agreement with, so they are outside of the cluster, so it's not so good. So the vertices we care about, they are not light. So we can remove all the plus edges between vertices that are light. And now we can just finish, like actually I said 4 steps, it's actually 3 steps. So it's like, now we just compute the connected components of the resulting graph. So we just remove plus edges between vertices that are not in agreement, plus edges between vertices that are light, and now we compute connected components. And that's your clustering. And that's a constant factor approximation to correlation clustering. So it's a very simple algorithm, 3 steps. And the beautiful thing here is also that connected components that you will get in this graph have diameter at most 4. So in fact, even computing the connected components is super fast. So that's very nice. And we can show, that's what we showed in ICML at ICML last year, is that it's a constant factor approximation. So it depends a little bit on this parameter for deciding how much they agree. Like, I made the proof with, I described the proof with 10%. You can change this 10% to, epsilon. Like there's a, maybe it should be smaller than 20%, but like, then you can make it smaller or larger. So there is a little bit of parameter tuning, but in any case, it's a constant factor approximation. And the good thing is that we made some comparisons on some graphs, and it's cool because it actually works. It's like, it's comparable to, it's much faster because the algorithm is so simple that, it doesn't spend much time doing stuff. And it can happen in parallel, it can happen in many seconds. So it's a pretty good thing. And it's at least as good as the pivot, for example. So the 3 approximation that we saw, in practice, it's not so much better. It's actually worse than our algorithm. So in fact, our algorithm has a better constant factor approximation guarantee in practice, it seems. And I'm not saying I'm just saying that, probably that's because in practice, what we are looking for are dense subgraph. And that's what our algorithm is tailored to. It's not that our algorithm is particularly smart, but it's like, it's doing the right thing in practice. And the interesting thing here is that, so last year with this paper, we were just looking at the distributed computation model. So we were happy because we got a constant factor approximation for this MPC model, which is like this distributed computation model. It was the first constant factor approximation in a constant number of synchronization rounds. So we're happy. We were also, as a corollary, we saw that we can do it like semi-streaming with constant number of passes. So we were happy as well. And then people picked up on that and, improved the algorithm and managed to adapt it to like get some result in sublinear time, like the first constant factor approximation for the problem in sublinear time, using very similar ideas. Similar for semi-streaming, just one pass, constant factor, very small memory, extending it. And we have 2 follow-up this year, and almost the same algorithm, just some kind of tweaks of this algorithm, gets you a constant factor approximation in the differential privacy setup with this algorithm. You can also do that. You can also do it like differentially private correlation clustering, constant factor approximation with an additive error that is optimal, like up to log n factors. And same thing with online with recourse, online where you have to decide online how you cluster, and then you can recourse if you change a node from a cluster to another cluster. Again, similar thing like all the one approximation with like optimal total recourse coming like up to log n factors. So it's a pretty robust algorithm, it seems, for dealing with many different setups. That seems to be working pretty well in practice. So that was like a pretty good story. And I'm going to stop here for the practical stuff, and I'm going to move into the theory before all the theoreticians have left the talk. No, I was okay. It's fine. I mean, and if I've not killed you already with the practical stuff, but if you have any question, like feel free to ask, and otherwise I'll just move to the next one.
Vincent, I have a couple questions. If you can go back to the last slide.
Yeah, sure.
Okay, thanks. Okay, so this I think I'm confused about how your algorithm is able to be adapted at all in an online or like an online with recourse kind of setting. Can you say a little bit more about that?
Yeah, sure. So so exactly. So we just in that case, what we are trying to do is like maintain the agreement. So essentially, we have this agreement between pairs of vertices, and that's kind of the key insight that we use in our algorithm to get the clustering. And what we can show is that for 2 nodes to be in agreement, of course they can change. Like the agreement can change. Like if you insert one node, one neighbors, they can become not in agreement again. But you can try to smooth this phenomenon a little bit, because whether you decide it's like 10% they are in agreement or like 5% whether they are in agreement. So you can make the agreement a little bit smoother so that it does not depend on one vertex, one neighbors. Like it has to depend on a constant fraction of your neighbors for defining agreement. And so in that case, you can make it a little bit robust. Like 2 vertices are in agreement, and to make them not in agreement, you need to change their neighborhood by a constant fraction of their size, essentially, of the 2. And so this can only happen like log n times. So if 2 things start to be in agreement, if you want to break it, then you have to insert like to double, like you can think of it as like doubling the size of the neighborhoods. So this can only happen like log n times, and then if you break the agreement only log n times for a pair of vertices, then you can show that then in total you're not going to change the cluster too much.
Okay, I think that made a lot of sense. Yeah, thank you. And then obviously this kind of idea of like smoothly breaking the agreement and then being able to go back and reassign to a clustering doesn't work in like an online setting at all.
Right? Exactly, because when you're online, then you have to make the decision, and then you can't really come back to it. So
okay, yeah, cool. Thanks so much.
Sure, thanks.
I also have a quick question.
Yeah.
So it really looks like Banzal-Blum-Chawla's algorithm, the very first algorithm that you described. I mean, what's the key difference that the algorithm that you described from this one? Also, can you give some insights why it is better than 3 approximation algorithm in practice?
So in practice, I think so in practice, I think the reason it's better than 3 approximation is that what really matters in this graph is that you look at dense subgraphs. So you have, I think in these graphs that we looked at, you have either very dense, like pretty dense subgraphs, and also a lot of singletons. And it's in the optimum solution. Like you have many singletons in the optimum solution, many dense graph. So our algorithm is very tailored to it. And if you have a lot of singletons, maybe the pivot is not going to work very well, because you pick a singleton and you're never going to output a singleton with the pivot, because if you have another neighbor somewhere, you're going to attract it and so on. So it's not, it seems that, maybe for practice is this, but I don't have a very, very good insight because this, so we tried on very massive graph, like that's also the issue with this graph is that they are really massive. And so it's hard to get a good sense. So what was the first question? Sorry, I missed the maybe.
Yeah, thank you. So the first question was that this key insights about like why you have quasi cliques with a small expansion. Like it reminds me the first algorithm, first constant factor approximation algorithm by Banzal, Blum, and Chawla. So I was wondering what are the key difference from this one versus that one?
I mean, that's a good question. So I don't know exactly the algorithm, but essentially here, yeah, I mean, yeah, actually, I don't know much the algorithm of Benson. So if you say a little more, I can say the difference. But yeah, hopefully rediscover what they have done. But
yeah, it looks like, yeah. I mean, as far as I remember, they also work on removing certain not edges, but removing certain vertices which has bad positive neighborhood, like small positive neighborhood, and they have singletons, and they have similar extra cost by dissolving those bad clusters after removing certain positive edges. So it reminded me of that algorithm. I was wondering.
Okay. Yeah, I mean, I should look it up. I mean, I think I went over it like. Probably the story is that I went over it like 2 years ago, and then I realized that I didn't know how to make it like parallel and so on, and so that's why we ended up with this. But I don't know exactly I don't remember the details of this algorithm.
Okay. Thank you very much.
All right, so let me move to now a more recent result that we just submitted. So this is to. Now I forget about practice. So now we are back to approximation algorithm. So now it's the big thing here. We are trying to get better than 2.06 approximation for correlation clustering. So we are trying to improve the approximation ratio of this problem. And as I said, so there is this 3 approximation, which is pivot based. And there is this LP rounding from 2015, which gives you a 2.06. And which is going as follows: like you solve the LP, and then you round the LP using a pivot-based approach. And what does that mean? That means that you pick a random vertex, and then you're gonna create a cluster for that vertex. And how do you do that? Well, you look at each other vertex and you put it in the cluster with a probability that depends on the LP value. You will do it probabilistically based on the LP value. And if you have a pivot P, you pick a vertex U. If it's a plus edge, then it's a function of how much it's separated on the LP. And if it's a minus edge, it's a different function how it's separated in the LP. And then after you have rolled all the dice on this thing, you get a cluster, you take the cluster out, and then you recurse on the rest. Okay, so that's the way you would actually round this LP. Okay, so here's the LP. Let me show you the LP. That's the LP. So you just have like the objective function, and for each edge, you're gonna, if it's a plus edge, you're gonna pay xij, which is the probability that ij are not in the same cluster. And if it's a minus edge, you would pay 1 minus xij, which is like the probability that they are in the same cluster. So that's the natural objective function you have for this problem. And you have this constraint, which is the triangle inequality constraint, which is the clustering constraint as usual, which is that, if ij are together, if rj are separated, then either I is separated from k or k is separated from j. Good. So then it's a triangle inequality constraint, so you can see it as a distance between the points. Good. So that's the LP. Good starting point. The bad news, the first bad news is that the integrality gap of this LP is 2. So essentially, when you have this star here, I only drew the plus edges. So this is a star of plus edges. All the other edges, all the other pair of vertices have a minus edge. And the distances I put on this star are like 0.5 on all the plus edges, and then let's say 1 on all the minus edges. So this satisfies triangle inequality, obviously. And now the LP cost is k over 2, and the integral cost is like, you can put a pair of vertices together. but that's the best you can do. And then everything has a singleton. So ratio of 2, it's a bad news because the ratio is 2. It's a good news because also the 2015 paper was almost optimal because it was getting like 2.06. So in fact, it's pretty good rounding algorithm. Good. So let's go and strengthen this LP. So one way to strengthen LPs is to use Sherali-Adams, so a hierarchy, to get stronger correlations between whether the points are in the same cluster or not, essentially. So we are just gonna have these constraints. So we are gonna do R rounds of Sherali-Adams. So that means that we have some consistency constraints, not only on like triples or quadruples, but like, we really need like R to be somewhat a large constant. And we will work with these variables that are like, for example, Y of S1 bar S2, etc., bar SL, which is the probability that the up clustering on a subset S is inducing the partition S1, S2 up to SL. So it's like, the induced thing. So, and of course, S has to be of size order R. For this to be, you can make it larger, but then the Sherali-Adams is not giving you much. So, but like here, if you want Sherali-Adams, then that's what you get. So for example, for a set of size 3, like, if you have like 3 points X, Z, T, the probability that X is separated from Z, they are in different clusters, is, probability that X and T are together and Z on one side, X is separated from Z and T that are together, or they're all in 3 different things. So it's like this type of things, this type of constraints that you will get. And if they are together, they are either together with T or they are together without T. Okay, so we have this family of constraints for sets up to size, I say R, but let's think of R as being like a function of epsilon that, will make our error. Our final error is going to depend on epsilon. So we have like, some function of epsilon, but like, let's think of it as a large constant. And we have the hierarchy ensures some consistency between these variables that I just described. Good. So the good news is that this star example that I gave you disappears. So we're very happy because we get rid of the bad example. The good question is, how do we round this guy, right? Like we get a solution from this hierarchy, but then what do we do with it? That's the next question, right? So here is the algorithm we propose and we analyze. And it's a little more complicated, but it's kind of inspired by the 2015 paper and the pivot rounding. So it's still a pivot-based rounding that is here idealized. So there's more details in the paper, but I decided not to bury you under the details. So let me just keep it kind of simple. And that's the algorithm. So you pick a random vertex P, okay, in your current set of vertices. And now you will look at the plus neighbors of P, and you will sample a random subset S of the plus neighbors of P in a correlated manner using the Sherali-Adams. And this is using the lemma of Ragavan-Rantan. Maybe you guys know about it. But essentially, this lemma gives you these two properties that, the probability that V belong to S is essentially YPV. And the probability that, if you sample like, V and U as plus neighbors of V, the probability that they are together in S minus, like the difference between like the probability that they end up being together versus YPUV is, some epsilon that depends on the number of rounds. So, we can think of this as being close to 0, still a constant, which is going to mess up our analysis later. But like, I'm kind of hiding this under the rug right now. This is not very, yeah, we had to struggle a little bit with this, but, let's say that this is like, pretty good. So we do this on the plus neighbors. And, on the minus neighbors, then what we would like to do essentially is that we pick independently each minus neighbor, we add it to this set S independently with probability that is something like 1 minus root PV. And then we create the cluster S, which is all these guys that we have taken, and P, depending on where, yeah, P. So that's the cluster. That's one cluster. That's on your output. Your recurse on the remaining vertices. Good. So the main difference that we have here with what was done before is that we have essentially, the main difference essentially here is that we are doing a correlated rounding on plus neighbors. That's morally what's happening. And we need, and to do this part here, we need to use Sherali-Adams and the Ragavan-Rattan lemma. Good. The analysis then is very similar to the pivot-based analysis or the pivot rounding that was also in Einlon, Charika, Newman, and that is in the 2015 paper for the rounding, which is a triangle by triangle analysis. So essentially, you will try to write for each triangle how much the algorithm pays. So you can write. You will play with these variables, which are like the cost that the algorithm is going to pay if U is the pivot, and for the edge VW. Okay, because of course when U is the pivot, we are very happy with the edge UV. We are very happy with the edge UW, which are rounded essentially as in the LP. So we are essentially optimal here. But then what's dangerous is that there is this edge VW that is rounded not necessarily as in the LP. And so that's why we need to bound this cost. And we want to compare this cost to how much progress we are making, because whenever we are creating this cluster, we are paying, but we are also reducing opt because some edges get settled. So for example, if an edge VW is going to be settled, if V and W are, at least one of them is in the cluster. If V and W are in the recursive part, then they will be settled at the later stage. But if either V or W or both of them end up in the cluster, then this edge is settled. So we want to compare how much alg is paying versus the progress. And essentially, we can bound with a little bit of calculation, we can bound the approximation ratio as the alg cost versus the progress. And essentially, we can do it triangle by triangle in the sense that we can look at the cost that the algorithm is going to pay when U is the pivot and when W is the pivot and when V is the pivot versus the progress that is made when U is the pivot, W or V is the pivot. So we can try to bound this ratio, and essentially you can show that if you can bound this ratio, you can get bound on the approximation guarantee of the algorithm. Good. And so there's a lot of calculation going on that I'm not. It took us a lot of effort, but eventually it's not that the most important part maybe of the result. And so essentially the challenge here is that what kind of bound do we get for this ratio with these triangles, right? And you can get different bounds depending on the different triangles. So if you have a triangle where all the plus edges, all the edges are plus, then you get a different bound than when they are plus, plus, and minus, or plus, minus, and minus, or minus, minus, minus. These are different cases that we have to, and we have different proof of the different cases. And essentially, we have to deal with the bad triangle. And the bad triangle is essentially a triangle that comes from the star example that we saw at the beginning, which is that you have more or less U, and then a plus edge 0.5 up to V, then a minus edge at distance 1, a plus edge at 0.5. And you can see that this satisfies triangle inequality. And we don't know, this is a bad triangle. This is something we have to deal with, because essentially here the ratio, if you do it naively, or if you do it as naively as we have done it, maybe if you are smarter, you can do it in a smarter way, but the way we can bound this ratio is just by 2. So here, if you want to stop here, you can get 2 approximation. So, essentially you get a 2 for these bad triangles, even with Sherali-Adams. So it's not that good. But remember that we want to beat 2. We would like to beat 2. And so we have this bad triangle where we have to do something more clever to handle them. And we have bad triangles that look like this. But if I perturb a little bit this 0.5, 0.5, and 1, like if one of them is much further away than 0.5, 0.5, and 1, then we start to be happier. Like the ratio starts to drop. So I put this gamma parameter here, and like, if we deviate by some function of gamma from these values, then we can get something that is better than 2. So we're happy. So it's really like when this is like, getting very, very close to these numbers, these 3 numbers, that we are in trouble. Good. So here is a way to get 2 approximation. And now let me move to beating 2. And essentially, we have this final observation. I should call it a Laymar rather. That is that, if you don't have if you have a non-trivial instance, it doesn't have only bad triangles. Because if we have only bad triangles, like overall, okay, let me actually phrase it this way. We are bounding the approximation ratio of each triangle individually. But in fact, the objective function is not the cost we are paying eventually in the correlation clustering objective is not the maximum over all triangles of the ratio, right? It's just it's like the sum over all edges, right? So in fact, here it's very pessimistic. Like if we are saying, okay, it's the worst ratio, then it's a very pessimistic view of it, right? Because it's not what's happening. What's happening is that we are eventually summing up over all possible edges. So what we are saying is that, okay, indeed, you get a 2 approximation if you had only bad triangles, right? I mean, if you have only bad triangles, then, you get into trouble, right? Because then the ratio for all these triangles is 2. So then you get, even if you sum over all edges, you get 2. Good. Now, what we show here is that it's not possible to construct an asymptotic instance, like a large instance, where you will have only bad triangles. So to show this, we have like, another definition where, we define like triangles PUV that we call chargeable if, maybe XPU and XPV are close to 1/2, but then XUV is not close to 1/2. Is not close to 1. It's like much smaller than 1. And in that case, the ratio is like 2 minus gamma. It's better than 2. And so we have this observation where here we use Sherali-Adams that, if you have a pivot P and then you have UV and that's a bad triangle, and then you have VW and that's also a bad triangle, then UVW is not bad. It can't be bad. So you must have, you can't have too many bad triangles, essentially. And eventually that claim implies that for all pivot P, the number of bad triangle PUV is at most the number of chargeable triangles P, U prime, V prime. So if you fix P as a pivot, the number of bad triangles you can have versus the number of chargeable triangles you can have is, the number of bad is bounded by the number of chargeable. And so now you get a trade-off because, if you go back to this example, like, if you were getting 2 for the bad, and now you're getting 2 minus gamma for the chargeable, then you get a ratio between the 2. Good. And so finally, the theorem we can prove here is that for any epsilon, and this is the number of, this is a function of the number of rounds you're going to make of Sherali-Adams, you can get a 1.994 plus epsilon approximation. So epsilon is arbitrarily small, right, as a constant. So you can beat 2. So you can show, and I think that's a very good example where you can show that indeed Sherali-Adams is providing you for a very important problem, is providing you a much stronger solution than the LP. That you really gain out of Sherali-Adams here, and you can beat the integrality gap. And that's it. I'm going to stop here, and happy to take questions.